is in our syllabus here according to BPUT, voltage regulation of alternator and load test and parallel operation and power angle characteristics, three-phase induction motor, no load and blocked rotor test, rotor, this wound rotor spring control and finding the efficiency calculation, single phase equivalent circuit parameters finding of an induction motor. So these experiments are listed. So I'll cover one from this side and one from motoring side, so that we will get accustomed to this theory. You just in the first experiment, I think the theory has been covered in the first day. How to calculate a MMF method, EMF method, and ZPF method. Another method is also conventionally existing. ASA method is also there. I did not include ASA in the syllabus, but these three methods are there. While coming to conducting the experiments, students may get practically many doubts, because what they learn in the theory that may not be same. They should get that in mind and they should conduct the experiments. Otherwise, what they do, they simply copy the circuit diagram and looking at the circuit and they will connect that. That way they cannot perform well, because practically when you are connecting circuits, especially in electrical power level circuits, if we are dealing with, everywhere we should take care of, especially grounding, these negative terminals, isolation, negative side, positive and negative neutrals. Otherwise, if there is a common neutral, then the risk is more. Again, for example, three-phase alternator, if we are conducting an experiment, alternator needs a prime mover. So practically prime movers are turbines and the other arrangements, diesel engines, etc. at the power station levels. But at the laboratory experimental scale, we employ any motor, simple DC motor or induction motor also we will do at some, because different colleges have their own setup. It is not mandatory that only this particular combination should be used, provided the machines comply the as per the standards, IEEE, NEC, IS standards. Combination it may be different. So one simple arrangement of prime moving is DC motor we use. So we give DC supply for a alternator circuit. Student may get a fundamental doubt like that. So it is for DC supply of the shunt motor we usually employ for the prime mover part. That circuit is completely different. And when we are coupling these two for the alternator, then actual analysis should be done on the alternator side. So student has to know first DC circuit why we are operating first. There is a starter. He may think that inherently for alternator DC circuit is required. Alternator DC circuit is required when field winding. For field winding, alternator DC circuit is required. So what we do mostly, same DC supply for shunt motor, prime motor, same DC supply we do it for excitation. This practice we are doing here, it poses some risks. If those are isolated, machine part, prime mover part and this excitation part, all are isolated, individual grounding. Say in our solar installation systems, we have arresters and we have inverter and we have battery and we have our household appliances. If the protection is given at each and every stage, that would be more protective. Right, one arrestor, one grounding, if they connect and leave, no problem, but problem may arise and it will cause severity. Right, so the minimum protection must be assured. So those experimental setup first should run in the mind first. How better we understand the experiments. One more thing, while connecting the meters, say we have ammeter in theoretically, if we say ammeters are always must be connected in series, voltmeters are always must be connected in parallel. Now practically if you see, first we will take the supply phase positive or otherwise, after that immediately we may connect it to positive terminal of ammeter or positive terminal of voltmeter. Right, which to connect first? Who should come first, ammeter or voltmeter? Or can it be either? After fuse, say, after the fuse or MCB, after that there is a DPST, double pole single throw switch, then we should connect the meters. right, at the measuring side. So which took, which voltmeter, ammeter? No, first to, you got my point, right? From positive terminal supply to ammeter terminal or voltmeter terminal. Which should come first? Which should come next? Can I know the reason why? Ideally, ammeter resistance should be 0. Ideally, because that is measuring current in series, so it should not take any drop. So that is why internal resistance, say, if we call that as ammeter's parasitic resistance, should be 0. Parallelly, when we are connecting, voltmeter should not draw any current. So infinite resistance must be there. Okay. Practically that is not possible. There may exist some least amount of resistance for ammeter, very higher amount of resistance in voltmeter. What is the difference?
Because if you connect voltmeter, it may draw some current and it may, so the net line current may.
Okay, in that case, when you are connecting ammeter, ammeter may have some drop, then the remaining drop will be given to the other circuit, then voltmeter reads lesser voltage. Correct. Solution is, both are valid theoretically and practically, depending on the accuracy level. Accuracy, how accurate. For low resistance load is connected, say, what this ammeter is reading, what range it is reading. If you connect low resistance side loads, then ammeter should be connected nearest to the load, because currents must be accurately measured. If you are measuring high resistance loads, voltage must be accurate. So voltmeter should be connected close to the load. That's the difference. These things theoretically, as we are discussing, both are familiar, both are the same. Practically, that is the usual practice. We connect first ammeter, then after voltmeter, because we are dealing with first load voltages we are majorly considering. So such points should be taken care while conducting the laboratory experiments. Again, DC supply and variacs, we have number of ways of getting this variable DC supply. Some get the rectifier with a variac, potentiometer we have. So separate ways are there. So if I draw the circuit according to our college setup, that would be valid for our students. For a different college, different student. But ultimately concept should be same. Based on that one common configuration, individual setups can be redrawn. One setup should be there in mind. One more thing. In the voltage regulation experiment, we are finding, finally, what parameter are we finding in any method? Armature resistance usually being neglected in theoretical calculations. For the calculation's sake, higher values, if they are present, lower values are being neglected. But armature resistance we are taken into account while doing experiments. Right. It is the synchronous reactance we are finding theoretically, that excess we are finding, then drops. Then after that, how much drop we are calculating from no load to full load, that gives us the voltage regulation. The way of calculating this is actually defining the errors. Why we have three methods? Among the three methods, do they give nearest values, means same values of voltage regulation? Are the voltage regulations calculated by EMF method, MMF method and this ZPF method, say three methods for example, can they be nearer or equal? Should they be? Accurate. EMF will give? Accuracy is less. EMF will give greater consideration of loss. Drop is assumed as more because these assumptions are there. We are not taking care of that in that method. Directly we are substituting as per the phasor diagram. So it will assume more drop from no load to full load. More drop is assuming it will give less accurate value, more error, more voltage regulation. MMF lesser than that. That is why one method is called optimistic method. I think you might have come across these words. Yes, these are interview-based questions. Students will practically put focus on this, right? One is optimistic method, another one is pessimistic method. Optimistic, expecting, pessimistic. Which one is optimistic? Which one is pessimistic? EMF and MMF. MMF is optimistic, correct. The EMF method is non-optimistic. It means pessimistic because these are general terms. To get the understanding of students' knowledge, they will ask these questions. In any competitive, I think you might have faced many of these, right? Because of these, we are getting the differences, these assumptions only. One more thing, finding the resistance of the armature winding. Resistance of armature winding, Ohm's law, simply, V by I. We have multimeters. Students will get nowadays, okay, all true RMS measuring multimeters are available. Okay, they take the 2 leads, put it in the range of what range they are going to measure. Okay, they will simply connect and they will get one reading. If that is the resistance of the armature coil, say, then why to go for this DC test, DC resistance measurement test. Before connecting to the open circuit test, first we conduct, right, in practice, measurement of armature resistance. How do we do that in experimental setup? We give some first lesser value of voltage, DC voltage to the armature coil, say 1 volt, say 1 ammeter and 1 voltmeter. Across the armature winding, we give 1 volt, 2 volt, 3 volt, maximum say 5 to say that is up to our number of readings, say less than 10 volts, but not like 200 volts, 100 plus volts, more than 50 volts. No, we give less DC voltage, then we take V by I values, right? Then we will get to some resistance, we are naming that as RDC. Then after that there is a practice of calculating RAC. Usually by multimeter student get one value. Then what is this value that he is measuring? Is it DC value or AC value or final value or what value? Usually it is the DC value. But practically if you observe in our records observations, there is a term called RAC is equal to some factor multiple times RDC. That factor, what is that factor? Why? Means it is showing that DC resistance and AC resistance are not same. Student will get no doubt. From his Ohm's law, he learned something. That is a coil. What is this AC resistance and DC resistance? Now there exists some concept. Yes, someone already told. Some effect, skin effect, right? When you are subjecting the alternating currents through the conductors, okay, at the machines, skin, yes. You are reading my next, I think you are completely prepared. You should have told that, then I would be happy to listen to you. Good. No, since I am being given chance here, I am speaking. Otherwise, I am open to learn from any experts here. There are people I can say, here only machines for subject dedicated experts are here. I am handling along with machines, power electronics, circuits and other, except power systems, many subjects I am handling parallelly. No problem. I am open for discussions. Knowledge by sharing, I think it's okay. Informal talk. This Vyaye Krute. I am not getting that. Vyaye Krute Vardhate Evam Vidyadanam Sarvadana Pradhanam. Nachoraharyam. I am getting this. There is a sloka in Sanskrit. Nachoraharyam, na rajaharyam, na bhratrubhajyam, na cha bharakari, vyaye krute vardhate eva nityam, vidyadhanam sarvadana pradhanam. It is the only education. It is the only intellectual knowledge that a person have. Upon distributing completely, it will double. Rest every asset will be deteriorated. It cannot be stolen by thieves. It cannot be stolen by Prabhu, tax. There is no tax. He cannot collect your knowledge as tax. And there is no correct. So I got that. So I am open for that. If you say I am actually learning a lot because of this interaction. Okay. So we are discussing resistance findings. So AC resistance, when we subject AC supply to the resistance, the windings, what will happen? The effective cross-sectional area where the current actually flowing is not entirely through the conductor cross-section. They are more prone to at the freely flow around the surface itself. So that is why effective cross-section area will reduce. Will increase, correct, yes, thereby resistance is increasing. We are getting AC resistance something different by a factor, as sir told, some value. Then we are finding RAC. Why now AC resistance we are calculating here? Because conducting experiment OC and SC test on alternators, right? So that is why AC term comes. So these are the main points. While conducting the experiments, the student will find on their own, which are not covered in theoretical sessions, right? So to find the voltage regulation methods, as we discussed in the theory, like that we have theoretical calculations, practically how they are going to conduct. One virtual lab sessions are present here. Now we will see. I am going to tell one more thing also. If I am not wrong, okay, we will see that here. Pre-test. Go for the pre-test. Okay. There is a quiz session here. Just 5 questions he told. Usually what we do, we ask students prepare something and we pose these questions. So first question, don't worry, I don't take much of your time. Just one experiment, I'll just discuss how actually things will work. If the power factor of an alternator under short circuit condition is almost near. What is he asking? Power factor of an alternator under short circuit conditions is almost. Okay. Alternator is now short circuited. Okay. He is asking what would be the power factor? Should be? Good. Correct. Yes. It is because when the alternator is terminals are short circuited, there is no other load is not connected. Alternator winding drop itself is acting as its load and the current is now flowing. That is purely inductive load. Purely. If you are considering okay, resistance also, but ideally it should be zero lagging. Click zero lagging. I am going to tell you one more thing after this. Okay, you just click. Okay, next. In a 3-phase cylindrical rotor alternator, 3-phase cylindrical rotor alternator. Okay, then field MMF, okay, leads the air gap flux and the air gap flux lags the armature MMF. Okay, next armature MMF leads the, okay, is asking the MMF relation of field and armature. Okay, can we guess any answer, sir, out of this? Field MMF leads air gap, armature MMF leads the air gap flux and the air gap flux leads the field flux. Field MMF leads the air gap flux and the air gap flux leads the armature. Yes. Any guess, sir? No problem. If you are wrong or right, this is not examination, I think, feel free. Sir, I request if any other participants can they can say, because they will, you know better than me, I can understand, but let other participants have some interactions. Yes, yes. Achha, our student is now giving an answer. No problem, we'll learn. See, field MMF leads the air gap flux and the air gap flux leads the armature MMF. As initially yesterday I talked, right, we are giving field excitation, it gets 1 MMF flux because of load connection. Armature gets 1 current, armature flux. How these two interact, resulting a torque excitation, right? They always in synchronous machines or induction machines or even DC machines, stator MMF and rotor MMF. Observe, stator magnetic field and rotor magnetic field, they always try to align with each other, right? And this rotate with synchronous speed. That type of alignment always trying to align, even though load side or at this any other disturbance happen, that trying to align is what generally is termed as synchronizing, trying to synchronize. That is why the term synchronous machines. Synchronous means what we you usually think of constant. Constant. What is that constant? Trying to become aligned. That alignment will result everything to maintain constant and stable operation. So, which one is first standard? Rotor MMF always rotates based on this prime mover. It is now assuming constant. Now stator MMF tries to align with the rotor MMF. Right. Now with this statement, can you guess? First, it means rotor MMF is now rotating. Stator MMF is trying to align with the rotor MMF. If it is not, torque tries to make to synchronize these two fields. In that case, first who leads and who lags? Can you guess up to this stage? Rotor field MMF. Field MMF leads. Next, air gap. Okay, we have stator MMF, rotor MMF. Resultant is the air gap flux, right? Now you come to this first conclusion. Rotor MMF leads air gap flux. Resultant. Next, when the resultant is behind the rotor MMF, how the stator MMF? What? Let me draw this. Yes, pen is here. Say this is 5M main field, right? Armature MMF, unity power factor, ZPF leading, ZPF lagging, demagnetizing, cross magnetizing, we are discussing, right? If it is a combination of say lagging or other, we have different phi A. Resultant of this is air gap, right? Resultant of this air gap. From this, what statement will follow this? Air gap
in between two.
You got the statement, right? Among these four, which statement satisfies this relation? Field MMF leads the air gap flux and air gap flux leads the armature MMF. Am I right? If I am wrong, please correct. I think option D. Click it. Next, cylindrical rotor synchronous generator. Cylindrical rotor synchronous generator will deliver maximum power output when? Okay. Maximum power output. Maximum power output means P EV by XS sin delta. Delta is the load angle, torque angle we are discussing. Load angle. In terms of load angle he is asking. Then when it would be maximum? Sin delta would be maximum. Right. So load angle is equal to synchronous impedance angle. Load angle is equal to internal power factor angle. Yesterday we discussed it. That's why I delta, phi, theta, and one psi is also there. Load angle means delta. Synchronous according to my notes, sir. You may have the different notation. Okay. Synchronous impedance angle. Theta. Next, load angle, internal power factor angle. Internal power factor, angle between E and I, psi. Next, 124, that is, what is 124? Wrong, I think this is a type of mistake. Okay, load angle again is equal to delta. I think yes, input power factor is unity. Input power factor. Load angle is 90 degrees, that would be the right answer. Yes, click there. This lab, this interface is designed by some IITs, I think, right? Okay, we'll see. Next, three-phase synchronous generator is operating at a constant load. Three-phase synchronous generator is operating at a constant load, okay? While the excitation is adjusted, okay, to give unity power factor current. Okay, excitation is maintained and it is giving unity power factor current. If the excitation is now increased, okay, excitation is now increased. I think we discussed this. When the excitation of alternator is increased, what will happen?
Leading power.
Excitation is now increased. Over excitation. Over excitation. It is now over excitation. Effect of armature reaction is when the over excitation. No, synchronous generator he is giving. Over excitation, what is the effect of armature reaction? Leading or lagging? No, take some time and then we'll get a conclusion. Because students will get knowledge in this way. Correct. When alternators are being over excited, I think I discussed it yesterday at this point, right? Alternators when they are over excited, effect of armature is demagnetizing. Then power factor will be.
If it is induction motor, then opposite.
Yes, this is synchronous generator concept. Then power factor. Power factor. Armature reaction, as you told. Again, leading or lagging? Lagging. Just like what load it is, excitation is given. Excitation is given from unity power factor. Where will it shift? Lagging side or leading side? Lagging side. It is the lagging side. Yes. Correct. Yes. That is the explanation. And it will become lagging. Power factor will become lagging as per our understanding. Okay. Next, synchronous motor. Okay. This part has not yet started. I think, okay, we can do this also. There is a numerical calculation. Synchronous motor with negligible armature resistance, okay, runs at load angle of 20 degrees, okay, delta 20 at the rated frequency, fine. If supply frequency is increased by 10%, okay, then keeping other parameters constant, new load angle will be 22. Yes. So you got this, fine, good. Click 22. So far our discussion, we have given almost right answers. Confidently. Can we submit? Lock कर दें. Submit. Next. नहीं, from the first.
और एक चीज में मुझे डाउट है, वो जीरो लैगिंग नहीं होगा, जीरो लीडिंग होगा.
क्यों? नहीं, आप ही तो बताए. You only told the answer as is becoming, sir. But it is showing wrong. What can be the? Yes. No. I am going to. That's why, na. I got also same thing. As per your analysis, I did the same marking. I got also same thing. This is why we ask. I used to do students. Ask the students. Students also got them. Sir, आप ही ने तो बताया ये मेरे को दो दिखा रहे. It can be wrong also, right? Why you think always these answers are given right? Even IITs can do mistakes. All are having mobile phones. All are having access to AI tools. Can you just briefly get the analysis? I have already done this. Can you confirm? Even after AI search also, what options we gave? That is the final answers. Why we test only IITs are supreme? Our sir is supreme here. It is a mistake from their side, right? When I wrote GATE examination, yes, people found at the coaching institutions, IIT question paper was wrong. And they wrote a letter from this Kharagpur and Madras professors who actually were conducting, they gave appreciation letters. Yes, we did a mistake. But I remember that question still in my mind. I don't discuss much about that. There is an infinite grid like this. Okay, some current is flowing here. Here say I. Some current is infinite grid, current is flowing from here. Infinite grid current should, when the circuit must be closed, what current it starts and that current it ends. I1, say I starts. Multiple times it may get splitted. Again, after closing the circuit, provided that the source is higher, same current should come. Then he asked in that question, I don't know which year, but before, very much before, those days were questions like this. He asked what is the resultant current somewhere. It should be same, but
और उसका अगर कॉमन रेजिस्टेंस आर है तो पॉइंट टू पॉइंट जितना रेजिस्टेंस हो जाएगा R/2.
correct. But in those options, they gave the key, right? I/2 they have given the options. Then the mistake was accepted by the IITs because infinite grid, when you are dealing with this, you cannot assume a positive polarity or negative polarity on the grid itself, on the grid plane itself. You assume positive polarity is somewhere at infinite and the negative polarity is somewhere at infinite. Some infinite to this flowing here, that means which is not in contact with this. You have come across this example, I think, earlier, right? Acha, good. You should have taught us also, sir. I would have recommended your name instead of, since we are lacking of experts here, they included me. Next FDP, I would recommend you to take this session, sir. No, generally speaking, we need experts advice, so that we will learn. Yes. Acha. Good. Thank you. Oh, good. Very happy. Yes. Under BPUT affiliation, we have an expert which is who has proven even IITs were wrong. Right. Very glad to meet you, sir, in person. We have experts here itself. Yes, we are right. IITs may not be right always. That point I understood after joining NIT. Before that, I used to think that whatever NITs, IITs do, they're right. They're right. They are also maybe wrong. And they admit that. It is as we feel fear. Who knows the background, who developed this? There is no disclaimer that, okay, we only did this, we are responsible. And many complaints were also raised. During Corona time, they made, I think, students' projects. These all simulations and all, they made it. David Halder, Fundamentals of Physics, sir. David Halder, yes, that textbook I used to read during my intermediate. So, similarity is matching much our knowledge domains. Yes, those textbooks I used to follow from my plus 2 note. David Halder and Resnick and Gerald Walker. Yes, IE Irido. Oh, okay, those are JE based. Okay, good. Glad to have that. Okay, these may be answers, what the solutions, what they gave may be wrong. We are right. These answers are right what we give. It is not 2 out of 5, it is 5 out of 5. That's what I wanted to say. Students' confidence badega. Apna confidence bhi badega. We should not change our minds once we are confident enough. Okay, if we do not know, we should admit. I admit. If I am wrong, okay, I am open to learn. Students should also feel that comfortability. Always lecturer may not be right. If he is telling something, we should accept. That is how we develop. Faculty develop. I believe. If you can differ with me, no problem. I am open, right? Next. Okay, all these calculations we found mistakes here. Okay, next, procedure. This is what experiment? Open circuit test and 3-phase alternator. Okay, now don't read the procedure, direct simulation. Okay. Drag that experiment 5 here. Just drag it, yes. Okay. Number of ways this circuit can be drawn. Here they drawn this way. Anyway, as I told, right, you might have your own setup at your institute. We have our own setup. He developed his own setup. Ultimately, open circuit test should be done. Before starting this experiment, let me introduce those who are not familiar with this as of now. Let me show. Alternator. It is showing RPM meter, speed measuring instrument. We call it as a tachometer. Okay. These are alternator output. R by V phases. Fine. Next, alternator should have a prime mover. That prime mover itself is motor output. What type of motor is that? Shunt motor. Okay. DC shunt motor. DC shunt motor. Okay. Next, alternator. Stator, we are getting the supply through RYB phases. Rotor, we should give DC supply as I am discussing. Okay. You see this salient pole. He has shown here. Okay. 2 pole. 1 pole. How many poles? 2 pole machine. Salient rotor type. He is giving excitation through, yes, DC supply. Okay. DC shunt motor. What did he miss, sir? Can any guess, sir? This time let us give other members of our faculty. What did he miss in DC shunt motor here? One important thing. In the circuit diagram, he missed something. Experimental, right? Correct. Big round of applause at least to encourage ourselves. Yes. Starter, he missed starter. Starter should be there. DC motors, when we connect starters, DC, LFA, mostly they are conventional starters. That's line, field, armature. Starters must be there. Okay, assumed starters are existing. Then DC supply. Okay. This is to find the open circuit test of alternator. What is the first step, sir? As per our known understanding, in order to conduct this open circuit test, alternator should be open circuited. We will measure the open circuit, and alternator we do the first next test short circuit. Thereby VOC by ISC we will get ZS. From there measured armature resistance square root of RA square, ZS square minus RA square under root will give XS. Substituting that into VI cos phi plus in that formula yesterday seen, then you will get finally the result. That is okay theoretically. What is the sequence of operation? If you ask students, mostly in conducting YY examinations, students start from the very first line, ask the procedure. We come across this, right? Connections are made as per the circuit diagram. That's it. After that, he'll remember, okay, we do this switch first, SPST switch first. There is a sequence of operation. How he should know without just cramming the procedure. Connections are made as per the circuit diagram. Okay, done. After that, what is the immediate procedure here? First, we should bring the alternator, prime mover to its rate, run at rated speed. Rated speed. After that, will it give directly open circuit voltage 415 line? Can we get the experimental? We are doing experimental, right? First thing should be maintained. Alternator should run at the rated speed. After that, field excitation should be removed. We should give in steps first. Not directly we will give 220 volt excitation. That is suddenly it will give open circuit. One by one we will take. Why? To take readings. Start from lesser value. That means initial field current. Field current. We are controlling here current. And we are talking about excitation, flux. Again student may get doubt. We are giving current. We are changing everything. We are talking in terms of flux rate. How flux comes by the supply of current? Electromagnetic. It is electromagnetic, magnetic field induced by electricity. That's it. That is how we are getting. See, it is, if it is a permanent magnet, we cannot vary this in this fashion. So, in practical machines, we use a exciter, DC shunt generators we generally use at these power plants as an exciter. Exciter means giving the field excitation by means of field current, IF. Right. After that, we close the field excitation circuit, then we will vary field excitation in steps. Then what to calculate? Field current and what voltage? Open circuit voltage. Again, we did not give any field first. We did not understand this point. These are some small points to be taken care while doing experiment only we will get to know. Okay, rated speed is achieved. I closed the field circuit, but I did not give any excitation. What voltage should it give? Ideally. Yes. Would it be 0? Practically? APRs, yes. Because there, even though we are not giving any field excitation here, already existing field may present here, maybe at small amount, because what, due to what property? That magnetic retention property. Right, you magnetize the material with some, that is how we got this BH curve, right, magnetic field intensity and magnetic flux density. You increase this with a rate, it will increase the other parameter. You try to decrease, again come back to 0, the other will not come to 0 because of this retentivity. Yes, the domain structure, it will not align as with respect to this excitation. Who is causing? Right, because of that field retains. That small residual flux causes EMF. That is how we are getting in DC generator OCC characteristics. We will clearly know that. Right. Yeah. Yes, because of that. Keeping those points in view, when we are doing experiment, okay, some value is shown. Student immediately asks us, sir, we did not give anything. IF at 0, so should start from this value. But it is showing some value. We may say that, okay, meter errors or something other. Initial days, I also used to escape for the first time, but later on I used to think myself, how is that coming? I did again and again, then I started learning, okay, there exists. Sir? DC generators. Yes. Yes, yes. Building is done by the DC shunt generator, but some value exists here. Yes. Is less, right? Yes, yes, yes. Three-phase alternator, the voltage is directly proportional to the excitation only. Because shunt generator, field winding and armature winding, they are connected in parallel. Whatever armature voltage is developed, that is directly being applied to the field. So that field is causing additional current, additional flux, additional EMF. Again additional EMF, additional current, additional field. Again additional EMF. So, and this process keeps on continuing within a very short span of time. DC shunt generator will develop its voltage reaching to its rated value. Yes. Correct, correct. Yes, that comes, that analysis entirely for DC machines. Yes, good. Yes. Yeah, KD, yes, EMF equation. Flux, it will generate. Correct. Yes. Mm-hmm.
industry they are running it, they are actually on good then. They are okay. So they are doing.
Industry.
In the
Manufacturing industry, I never tested, sir. I never been to. They're giving these calibration reports. They'll say that. I think practically they should do, but that alternatives up to that level they do not do. But how they are doing, so maybe if they could share their details, then we might be known. But I never experienced industry how they are calibrating. Correct. Yes. How they are. Yes. It is just like how the IC, what is inside the Intel processor, how they are making those any EQ. That is their what you say IPR or their own method of way. But there should be some industrial method, but which I am not aware of. Definitely, I will take this point now. Consider. I will try to learn that. Then, if possible, then I will communicate at the industry level how the actual testing is done. Yes, that part I will try to get to know. Okay, that's it. Only these are the observations. After that, we will change the. We will conduct the experiments, and we will take the readings and. We will take the readings up to some saturation level so that open circuit voltage characteristics are done. Now you can close just one reading. I will show later on. Now you are familiar, I think, right? You can do this. Yes. Now, what to be closed first? This. DC. Alternators, prime mover. First we should bring this into rated speed. So close this. You please keep the close this. Then you change. Okay. Change this to here. You click here. That's it. Yes. Observe here. Okay. 138. Next. It should come up to rated. Okay. What is the rating? Just slide this a little downwards. Downwards. Here inside. No, here this point. Yes. We insist students, not only circuit diagram is sufficient, up to what speed we will increase. That depends on my alternator may run at some speed. Your alternator may, your college, your institute may at some speed. Say your ratings may be different. 1 kVA, I have 1 kVA alternator. You might have 11 kVA, 5 kVA, 3 kVA. If you are affordable as sir expressed is concerned, someone who is capable of putting an industrial alternator, they might have get 10 kVA and above. How to know? By only nameplate details. They should write under the circuit diagram nameplate details. They are must, so that they will know up to what range they will operate this machine. Alternator ratings, if you observe, he has considered 3 kVA alternator, phases 3. Speed is 1500 RPM. Okay. Yes. Okay. Quickly we will see other ratings also. Okay. Wait. DC shunt motor, which is prime mover. It is a 220 volts DC motor. Armature voltage. Okay. Max 440. 5 HP. Field current 2.3 amp. This should be taken care. And armature current 9.5. Its speed is 1500 to 2000. These two should match. Okay, he considered these IEA armature current of shunt motor, armature current, armature voltage, field current and open circuit voltage. He, according to his notations. One reading we will take because it will take a lot of time to reach this. Now this, yes, sir. Yes. Motor, yes. Sir. What he has taken, yes. 5 HP. Alternator 3 kVA. Yes. Sir has rose one more interesting point. 5 HP motor output. Ideally, how much should be the alternator input? Ideally, 5 HP motor output is coupled to alternator input. That means motor output should be equal to Alternator input, motor rated power is 5 HP and alternator rating is 3 kVA. Are they same?
What is it is in kVA?
Okay. What is causing the difference? A little more. 5 HP is not equal to 3 kVA. Why? Power factor, good. This is what we are expecting, because output can never become equal to input. Losses as well as it depends on power factor also. VI cos phi is equal to our active power. So if you multiply that 80%, say 80% of that rated may give. That is why if that is 3 HP, after this say power factor and the and efficiency, then alternator must be in that range. Yes. Yes, correct, because it is the primary source. Prime mover is the main source for the alternator input. If you have something at input side, though the losses may occur, rest can be assured, so that the alternator will get sufficient power input, right? That's it. Next, we will increase this up to 1500. Okay, assume 2-3 steps. Okay, we should at a time take care of only speed, not speed. What is to be taken care? We are changing currents here. Currents, voltages we may, that is also not allowed. We may increase beyond the rated on open circuits, but currents, it is the current in entire electrical engineering should be taken care of. Every time we say short circuiting, currents, short circuiting collapses everything. Even at the short circuit happens. We got this in many news every now and then. Short circuit happened, fire accident. Short circuit happened, something damages. Short circuit is resulting what? Current, infinite current. That should not happen at all. It is just like heart attack for human beings. That should not happen. So currents, rated current is given. When it is reaching that value, simultaneously we should observe. Speed is reaching or not, at what value. If it is near to rated current, we should slow the process. Yeah, yesterday our HOD sir was telling in the hydraulic power plant control system guide vanes, how the water flow is entering. When the load is approaching, okay, we have to give more input. How? Not all of a sudden, because that is a water flow through the penstock. Penstock water flow control is not that easy that you will suddenly close everything and you suddenly open. No, penstock will get subject to more pressure. Right, that entire system must be balanced in all aspects, mechanical and as well as electrical aspects. So we should take care of currents below the rated, above the rated currents. Okay, we should take care of. Maximum current is reaching means, okay, we should carefully observe. Next, okay, assuming that this is reached to 1500 RPM. Next, what to do? Go up. Okay, we are observing here. Now you see, VOC is giving some value. We did not close this. Okay, at this point they made this circuit diagram correct. There may be computer mistake, their algorithm mistake, or this website mistake. At least they have taken care of these concepts. What we are discussing, they did this. Okay, now you. Okay, after reaching this into rated speed, now what should be given? Field excitation. Yes, close that. This is done. Okay, it will take so many steps. So for each step, there is a recording process. Store data. Okay, then now close it. Now we are giving field excitation. That will increase open circuit voltage. Now increase. So 0. 24. Okay, now next. Okay, 0.2, 40. Up to what value? Up to what value? One more thing. Again, see, one experiment, how many points we are discussing. What voltage will give? Okay, you open this. Rating. Okay, rating. Yes. You please tell me. Zoom it. Okay, this voltmeter is connected between R and Y. What voltage now we are measuring? Line voltage. So up to what value we should increase this? Correct. We should see the now go to the specification, nameplate details. The nameplate armature voltage is 415. What voltage is that? Usually when nothing is given, we should consider that as a line voltage in case of 3-phase. So that is line voltage. One more observation, good observation. Yes, like this when you are conducting, you will get to know how long, how value. Once it reaches 415, okay, open circuit, some more percentage of it, say 25% or what maximum that will be given by the manufacturer again. You cannot increase open circuit up to 415, say 800 some other thing. No, saturation will happen. Beyond that we should not excite. Okay, that's it. Open circuit done, and below this there are readings. Just down this. Yes, or yes. Now start storing data. Each reading. Okay. So this show data. Further. Okay, the tabular column now gives what readings students take. Otherwise, VI, where to keep 230, where to keep 0.6. In place of V, he will put 0.6. In place of I, he will put 220. We will give simply, no, it's wrong. Students should know. Right, this way they will practically interact and learn more the theoretical concepts what they learn. Phase, line, power factor, again armature, reaction. Many concepts are covered within one experiment itself. Right? That's it. Sir? Starter. Starter, which starter, sir? Show the circuit diagram. Here. Third, zoom out, correct? Zoom out. This. Acha. Yes. Acha, you are asking that which control you are which method you are controlling the speed. Good. Acha, by which method you are controlling this speed? Okay, can you guess which method is now? Wait. No, what is required? We have two methods of speed control for DC machine. One is flux control and another one is armature control. So speed control we can employ either armature voltage control and field control. What method is employed? No, what should be employed? Sir's question is that, na? Now I am in turn expressing the same doubt. And others we may. Both.
Because if it is not coming, then we have to bring at 1500
Okay.
So both will be there. If it is decreasing, then we can increase.
Okay. Wait, sir. I got sir's point. Let us take others' opinion. What method should be employed here? Shunt, field excitation or armature? Why not field? Wait. Okay. Any other idea, sir? Sir, why I just told you to not to talk only for that particular time. If you are stopping, we are lagging. Please help us. They are asking what method of speed control for this DC motor should be employed to meet the alternator prime mover rated speed. whether it is, this is motor control only, right? Sir, you miss your option, sir. Okay, he got his, I think, correct. Yes, so what method should be employed? He got his point, yes. Little appreciation for our another senior faculty. Good. So what should be employed? Speed control can be happen in two ways. To control either below the rated speed or above the rated speed. What control should we adapt now here? So, okay, which method is for what control? If it is below the rated speed, what speed control method is useful? Armature voltage control. Okay. If we want speed above the rated speed, what method do we use? Flux control. What speed do we have to use now? It is so initially what should we give? 0 to 1500 or from higher to 1500? So 0 to 1500, what method should be employed now? No, I need one answer, sir. Okay, again, which method is used for above the rated speed? Which method is used for below the rated speed control? In this alternator speed control method, how we are controlling below the rated speed or above the rated speed? We are making it from 0 to 1500 or some other higher value to 1500. 0 to 1500 is below rated speed or above rated speed. So below rated speed, what method should be employed? Armature? Again, final, I need all collective one answer. Sure. This time sure. This is armature voltage control. Yes, yes.
From 0 to 1500 we can also take.
Where?
Cross control.
Flux control. 0 to 1500.
Above 1500 we will get.
Yes.
0 to 1500 we can take. Na? So,
No, the
yeah, it is possible.
the field winding blast control method, blast control method, you have to add external resistance.
Correct. Usually, yes, your idea is correct, sir. We can have that flux resistance control method also, provided which flux will give maximum. EB is equal to Z pi P n by 60A. If you keep the generated voltage, flux and speed relation. Flux and speed will directly proportional to EB, inversely proportional to flux in case of DC machine. I saying increase the flux, decrease the speed.
Actually, in this case, what is our main aim? We have to fix that for 1500 RPM.
1500
Any
RPM.
method we can take.
Practically, which should be employed? We want to make it from 0.
So,
Yes, theoretical will be made. We are doing experiment, right? So when we are trying to make the alternator to rotate at rated speed, let us start from its 0 output. No voltage to DC machine, armature, no currents, no speeds. Increase the voltage slowly so that output of this motor will increase directly. Simply it is getting possible. So that's safe operation. One method which we are trying to employ here. It is not that we cannot use general practice of conducting this experiment under safe conditions. We are employing armature voltage control method. As this sir expressed, field control. Additional to this, yes. Yes, if a flux is higher, then speed would be lower. Flux is higher means field current should be higher, DC field current. DC field current should be higher means DC field resistance should be lower. Initially itself we are getting high currents. In that case, initially we are getting high currents, right? Our objective first currents must be taken care first. So to that practice, voltage, zero voltage, okay, from gradually we are weighing by means of rheostat, safest method. Accepting in practice method, we are controlling armature, because high to avoid that high currents at the starting, we always starts from zero, slowly. From higher, if we take suddenly, starter may get sparks. If you, in order to start the field winding at the say rated current, starter will get sparks. So to avoid such complications, we commonly adopt this method. Am I right, sir? Or you can differ if, okay, fine. Thank you. That's it, sir. Open circuit test. Okay, now short circuit test. Just after knowing this, short circuit test, even that should be taken more care. Short circuiting. What common mistake students will understand? Here you made it to up to 400 volts open. After short circuiting, what students think? Make it up to 400 volts. Then short the armature terminal. Students generally think that short circuiting current means they may think, okay, I used to practically show them, okay, we increase now 415, short circuit, let us close, they will say close. We should not close at rated voltage alternator output. Why? Short circuit as the first question, that is why the first question, right, in the pre-test he showed what is the power factor of the alternator when short circuit is happening. Short circuit current will flow not at the rated value. Short circuit current will flow at a very lesser value of a terminal voltage, because resistance is zero. Even at 10 volts we will get short circuit, 1 volt we will get short circuit. So that is usually not short circuit current. Short circuit current is infinite, right? So practically what short circuit current means, this is very much important. Short circuit current means we are having some value that is, okay, that should not be beyond its rated current. Rated current, so what is its rated current? I think it is 4.3 some say amperes. Your short circuiting current, even though alternator output terminals are short circuited, current flowing through these phases should not exceed more than 4.3. Say 25% of it may be allowed. You usually say 125%, if I am not wrong the number. Beyond that, no, alternator windings cannot withstand such high current. Then how to get that limited amount of short circuit current? Only by reducing the output voltage. Right, that is why alternators, while doing short circuit, first you should ensure that voltage is now zero. Then you slowly increase. What increase? Excitation, good. Excitation when you are increasing slowly, next this open circuit, this now voltage will cause current, and then we see the meter reading, which meter? Ammeter at the short circuit terminals. That point is utmost to be taken care. If that is reaching 4, okay, still, then we should take care of this. Since we are dealing with analog meters only, if it is reaching that value immediately, okay, motor is now operating under full load. One more observation. Is this generator is now operating at full load or no load? Under short circuit condition, full load. But are we actually loading? Sir? Yes. But how? See, we are not actually loading the machine. Here I got the answer that sir has expressed, right? Short circuiting, by short circuiting the alternator, by providing the minimal voltage generation, then they are conducting that full load condition. Transformers we get this, because actual loading of the transformer at MVA range, KVA range, full load efficiency, off load efficiency, how do we calculate? They manufacture. I think in India we have BHEL, Bharat Heavy Electrical Limited is the company who manufactures these equipment. Every equipment what they manufacture, they cannot load it in the field and then they test and they again pass the certificate. Okay, we calibrated by actually loading. No, they test it. How they test? Short circuit test. That is these are tests. by providing small voltage by varying the excitation. That's it. After taking care of that, sir, here it is open circuit, short circuit test, another experiment is there. He has shown, because showing this, I just given some inputs for that. Now, I think open circuit test, okay, just to show the short circuit test. That's it. Short circuit current, okay, at what excitation we are getting, IF, we will note that field excitation as well as okay, short circuit test, okay. Then take the reading. So VOC we got it by here. ESC we get by this experiment. Okay, directly go for simulation. Here also again for each and every test experiment they give some pre-test question. Same one experiment, all are similar. So we are discussing deeply. Here you can observe this. This is the ammeter connected from R to this way. Again, where to connect? If you connect at this point, between R and Y at this point, what will happen? Again, this point, what will happen? We are connecting ammeter. It depends on alternator, armature, winding type. Again, fundamentals. We can tell the students that the use of star delta transformation now comes into picture. If it is delta connected, what voltages and what currents? If it is star connected, line currents, phase currents, similar, same, and line voltages are different, √3 times of phase voltages. We use this in starting of three-phase induction motors. For the same power rating, we get reduced voltage which is required to reduce the starting currents in case of motors. Right, that depends on the connection. So here we connected. That's it. Rest of the experiment completely is same. After finding this, we will get the what VOC by ISC and plot and any regulation method if you want to follow, say EMF method primarily, then we will conduct the experiment. Now after understanding this, now everyone can do the experiment in your own institutes and in other institutes also. You go to other institutes, even any other, just you see there, you must be familiar with their nomenclature. They may call it as 1, 2, 3 phase. In European countries, they follow UVW culture. U phase, V phase, W phase. We follow RYB culture. Just to see the nameplate details, okay, observe their manufacturing style, how they did it, just start connecting. Right? The same way, students can also, upon repeated practicing, they can also perform well. Right? For all experiments. Can we go for another experiment or shall I keep it for next session? Okay. Okay, again the same thing students feel when we teach in our institutions also. Now you understand the pain. Right. How students, we usually always blame students. You are not interested, you prepare. I know the faculty, the hard work of the faculty, even I am in the same field, right? I may be a junior among all of you, but still, now you are understanding, right, the pain of continuously sitting and listening, though it may be interesting or not. If it is interesting, still that resist, that opposition is stopping. If it is not interesting, you think how much pressure student is now handling. Yes. Yes. I'm just kidding. To understand this problems from students' side. That's it. Okay, today it's my mistake because of some administrative issues. I got delay. Tomorrow, first half, Kevin Manthi sir. Yes, so induction motors may be continued. Tomorrow, second half, again I have to see first. Anyway, we will communicate through groups. I will say yes. Anyway, we will communicate in the. You have a common group, right? For the development, we will. Otherwise, if you want, as per your wish, also we can proceed.